All right, so we're going to spend a large portion of the last final month of the class talking about light. And so we're going to start by talking about light as a wave. And so that's really an issue of talking about electromagnetic waves. And so to set this up, let's again return to something that we learned in 221. What is a wave, period? Right? So just in general, what is a wave? Well, it's a mean of transferring energy from one point to another without transferring matter. So if I take a string, tie it at one end, and then grab the other with my hand and wiggle my hand up and down, then obviously I'm doing work on the string as I wave my hand up and down. That energy from the work I do is then transmitted along the wave as this, in this case, wave pulse moves along the string. So I did work. That energy gets transmitted by the wave traveling across the string. Now, in 221, we focused on a particular type of waves known as mechanical waves. Mechanical waves are defined by the fact that they need a medium of particles to travel through. So water waves travel in water. Sound waves travel in air or water, or some fluid, or it can travel through a solid. But sound waves have to travel through some medium. Seismic waves, obviously these are waves that travel through the Earth's crust, travel through the Earth during earthquakes. Waves on a string, obviously they travel through the string. So all of these are examples of mechanical waves. All of these mechanical waves need a medium of particles to be able to travel through. Electromagnetic waves, on the other hand, do not need a medium. They can travel through vacuum. So they are able to travel in an absence of particles. So the fundamental question becomes, so if there's no medium for electromagnetic waves, then how do we create them? And the idea is fairly simple, and it builds out of what we've been putting together in terms of talking about electricity and magnetism. So we know from Faraday's law that varying a magnetic field, or we've at least talked about how varying a magnetic field with Faraday's law will generate a current. And a current, of course, is simply charges moving in response to an electric field. So Faraday's law can be kind of restated as telling us that a varying magnetic field is accompanied by a varying electric field. There's another law describing things that go on with electricity and magnetism known as Ampere's law that also tells us that varying an electric field is accompanied by a varying magnetic field. So you notice that basically what both of these two laws, what Faraday's law and Ampere's law tell us, is that if you change one type of field, whether it's magnetic or electric, it's going to generate the other type. And so basically what we're going to do is we're going to form electromagnetic waves when we vary an electric field, and that's coupled with a varying magnetic field. So in this picture that we see here, the electric field vectors are the blue ones that point up and down. The magnetic field vectors are the red ones that point side to side. And then the wave travels, in this case this is roughly drawn to be sort of coming out of the page at us. So we've coupled an oscillating electric field with an oscillating magnetic field. Now, fundamentally, just to make sure that we notice, the electric field and the magnetic fields are perpendicular to each other here. Right? So where one is big, the other is big. Where one is zero, the other is zero. So in terms of the oscillation, their strengths are related, and they're perpendicular to each other. The other thing that's important to notice from this picture is that the wave actually travels in a direction that's perpendicular to both of the fields. So if the electric field's up and down, the magnetic field's side to side, the wave is going to be traveling into or out of the page. So electromagnetic waves travel at a constant speed. In vacuum, that speed is given by c. So this is the same c that you guys know from the equation E equals mc squared. C is the letter we use to represent the speed of light. And it happens to come from 1 over the square root of epsilon naught was our electric constant, mu naught was our magnetic constant. So the fact that you literally you can calculate c straight from using the two constants that we used in doing our electric problems and our magnetic problems is part of what's again, just reinforcing the idea that an electromagnetic wave is built up of both electric fields and magnetic fields. And so when you calculate this out, you get a value that's basically 3 times 10 to the 8th meters per second. And this is the speed at which light travels in vacuum. We'll see a little bit later that we can figure out what the speed light will travel in any other medium. But when we talk about the speed of light with this value, we're really talking about how fast light travels in vacuum. Now, since I know that light travels at a constant speed, I can use that speed to figure out the distance that light will travel by the same equation that we use to describe the distance for anything traveling at a constant speed. So for any object traveling at a constant speed, we had this equation that told us that the distance equals the speed times the time. And all we're doing is saying that if I want to deal with this in terms of an electromagnetic wave, now I have a special value to plug in for that speed, and so the distance an electromagnetic wave will travel is just going to be the speed of light times time. So that's one way that I can think about the speed of light. The other way that I can think about the speed of light, so the way we were dealing with before told me something about how that light is going to travel. This tells me something about how that light is sort of made up. So here I have a second equation, and what it tells me is that the speed of light is also equal to the frequency of the light times the wavelength of the light. And so the frequency is either going to be in hertz, and hertz is another way of saying inverse seconds or 1 over seconds, and then we're going to put the wavelength into meters, and so of course if I take something with meters and multiply it by something with 1 over second, sure enough I'm going to get a speed in meters per second. But what this is telling us is that the speed of light can also be used to relate the wavelength, right? How far you have to travel before the wave starts to repeat itself, to the frequency. And so if sort of here is one cycle, right, the frequency is telling me the number of cycles that occur per second. So the wavelength tells me the distance I have to travel, right? It's literally a length that defines how far you have to go before the wave repeats itself. So a distance I have to travel, how far do I have to go before the wave repeats itself, and that's related to how often the number of cycles that the wave undergoes each second. Now the other parameter that's sort of in this plot here is that, well, the amplitude is telling you something about the power. So when we were thinking about creating our electromagnetic wave, the easiest way to do that is just to take some charge and start to wiggle it. And so as I wiggle it up and down, it's going to create this electromagnetic wave. The more I wiggle it up and down, the more energy is required by me to do that, right? The more work I have to do. And so the amplitude is telling me something about the power. So when I think about optical, or sort of what we think of as visible light, right? So the light that we can see, you notice that I go from red, yellow, green, blue, violet, and looking at sort of the different colors of light, what I see is they've got different wavelengths, right? So red is actually on the long wavelength end, and then as you go sort of from red to yellow to green to blue to violet, the wavelength gets shorter and shorter. So what this equation then tells me is that if I know something about the wavelength, then I can figure out what's happening with the frequency. So you can see that when we look at the full spectrum for visible light. And so we know that all of this is going to move with the speed of light. That speed of light value is going to be constant, which means that as we go from violet light, which has a short wavelength, high frequency, to red light, which has a longer wavelength, lower frequency, that we're going to go from one end of the spectrum, right? So violet's going to be at the high frequency, short wavelength end, which means we're still going to get our value C with a large frequency value and a short wavelength value, versus red, where we're going to have a low frequency value but a long wavelength value. So C is going to be the same for both of these, and basically what we're changing is just this F. We're changing the frequency and the wavelength in such a way that it keeps C constant. And that's going to be true for all these other colors as well. So that as you come down from the high frequency in, the frequency gets smaller and smaller, but the wavelength grows in just the right way so that the speed of light stays constant. Now we said the visible light's just a thin sliver of the overall electromagnetic spectrum, and so here's a situation where, so visible light, the high frequency end is violet, and you notice that just above visible light is ultraviolet, which is basically frequencies just larger than violet light. The low frequency end of visible light is red, and just below visible light is infrared. So these are frequencies that are just smaller than red light. And again, for all of these in the electromagnetic spectrum, gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, radio waves, for all these types, all these forms of electromagnetic radiation, they all travel with the speed of light. So again, we go from the high frequency short wavelength end, up here with gamma rays, to the low frequency long wavelength end, down here with radio waves. And so again, for each of these, basically as you come down from gamma rays, the frequency drops and the wavelength gets larger. Alright, so here's sort of where you can see that thin sliver of visible light sitting in the entire electromagnetic spectrum. And again, you've got your high frequency short wavelength end over here with gamma rays, and your low frequency long wavelength end down here with radio waves. And what's interesting about this particular picture is it shows you the things that are roughly the same size of that wavelength. And where this matters is that one of the things we'll talk about how light and matter interact is through scattering. And basically, light scatters with stuff that's effectively the same size as its wavelength. So X-rays scatter off atoms. Right? So you can get X-ray scattering off the atoms within, say, some crystal structure. Radio waves scatter off large things. So the idea of sitting and listening to an AM radio station, and that station gets fuzzy as you're driving around in your car, you may pull up to some light, and based on where you are and how that radio wave is being scattered by the buildings or the trees or some other large radio wavelength size object, it's scattering off things that are that size. So the size of the wavelength matters because basically that tells us what kind of matter it's going to interact with. So all these things are things that we want to pay attention to: wavelength and frequency.